Why do we test or evaluate things? We need to verify that our design and development effort has been successful by confirming that our design has resulted in components, then subsystems, and then eventually a system that meet specified requirements. This helps identify areas where redesign might be necessary. This sort of verification is sometimes called developmental test and evaluation, or DT&E. An example of component testing might be to test different types of concrete before deciding on what concrete type to use in critical areas like footings or slabs. We would then test the concrete as it arrives on site prior to it being poured into the excavations. Although it would appear to be inconvenient and might even upset a few people, it's much easier and cheaper to reject poor concrete before it's laid rather than discovering structural problems after our house is built, requiring expensive and time-consuming rectification action. As the system passes through production and construction, we need to verify the acceptability of the system against our system-level requirements. This sort of verification is often called acceptance test and evaluation, or AT&E, because the aim of this verification is to allow the customer to formally accept the system and the fact that it meets the system-level function and performance requirements. Acceptance testing will be a finite period of time and will involve both customer and contractor personnel. In our house example, it might be dominated by a period of just walking around the house and having the different key elements of the house ticked off. This would be a series of demonstrations, inspections, and tests, to use the terms we came across before. Once the system enters the utilisation stage, we continue to evaluate the system. Generally, this sort of evaluation aims to continually validate that the system is solving the problems that created the need in the first place. Naturally, this sort of exercise involves the system being employed in operational environments, being used by end users who are trained by our training system, supported by our support system, and so on. As we live in our house, there are bound to be things that we don't like about it. For example, we might find out something about our house that was not apparent during the acceptance testing that means that our house does not actually meet the specified requirements in certain areas. In this case, we would probably have some recourse against the contractor in the form of latent defects or warranty provisions in our contract. We would use these provisions to have the defect rectified. In other cases, there might just be things about the house that we would have done differently if we'd had our time again. These experiences may raise issues that result in modifications or upgrades to our system. Modifications and upgrades are an opportunity to reinvigorate systems engineering as far as the system goes, as upgrades may be considered to be a system in their own right. Validation occurs when we take steps to confirm that the system achieves the purpose or need that kicked the whole process off in the first place. As we go through the systems engineering process, we should always keep validation in mind. For example, when we think that the system requirement specification is good enough from a requirements perspective, we need to make sure that it is in fact going to result in a system that meets our stakeholder needs. This process continues down the requirements hierarchy. Naturally, when our system rolls out of the production and construction process and enters operational service, we will be able to confirm or validate that we've got it all right. At this point, we'll combine our system with our people, with our support environment, and so on. We will be using our training system. We'll be interacting with our external systems in an operational environment. If all of this adds up to satisfied stakeholders, then our system is bound to be validated. If not, we've got a problem. This is why, as we go through the systems engineering levels, we must continually look back up and make sure that we're not only doing the job right, but that we are still doing the right job. Verifying and validating the system in this way is a risk mitigator because it allows us to confirm design adequacy, detect problems early, confirm rectification action, and so on. In other words, it helps protect us from ending up with a system that doesn't work the way it was intended to work. Leaving this sort of verification and validation exercise until right at the end of the production process is leaving things too late. Progressive evaluation is the key. We mentioned examples of verification methods in earlier modules. For example, we spoke about words like test, demonstration, inspection, and analyses to perform verification activities. Programs to adequately evaluate a system must be planned and managed. If they are not planned and managed, there will be serious ramifications, such as project cost and schedule blowouts and acceptance into service of poorly evaluated systems, simply because evaluation can take a serious amount of time and money. The sorts of things that need to be considered include specialised facilities and test equipment, personnel availability and training, approved evaluation procedures, availability of necessary external systems for the evaluation program, and so on. If these sorts of things are planned properly, we will not have to repeat evaluation unnecessarily either. This will also help save us time and money. The bottom line is that evaluation is a critical part of systems engineering, and it must be planned and managed right from the very earliest stages in the systems engineering lifecycle. In my experience, if this planning is not done, you'll be left with a couple of very undesirable choices to make, such as, do I blow the project cost and schedule to ensure that the system is adequately evaluated, or do I deliver a system on time and budget without thoroughly evaluating it? You'll have to admit that these aren't great choices to have to make, so avoid having to make them by planning the evaluation process and allowing for it in your cost and schedule estimates. Configuration management is a very important part of systems engineering. It's there to make sure that we maintain control over the versions of all the different things within our system design. This includes our documentation, like specifications and drawings, and the hardware, the software, and the interfaces that make up the design. For example, it's critical in building our house that all parties involved in the house are running off the same set of drawings and associated descriptions. Imagine the difficulties that would be caused if the customer, architect, and builder all had different versions of a document that listed the windows to be installed in our house. This could happen if changes had been made to the documents without involving all of the parties in the change process. That sounds absolutely unbelievable, right? Well, I've included it as an example because it's happened to me, so I can assure you that it is possible. Configuration management aims to avoid this sort of problem by establishing and maintaining configuration control. There are 4 basic elements to configuration management. Firstly, we identify everything that we're going to place under control. In our house, this will include the set of drawings, specifications, and other documents that will be used on the project. Only those drawings listed are authorised for use. This will also include pieces of hardware and software that are used in our project. For example, the make and model of the washing machine, oven, hot plate, and security sensors are all examples of things that are likely to be specified and agreed upon. In terms of software, it's possible that integrated entertainment systems, security systems, or automated watering systems will all make use of specific operating systems and other software. It might be that the version of software running on some of these computer-based systems is also specified and controlled. Once we've identified what we are controlling, we then need to be able to communicate that to all parties. We do this by being able to communicate what the current configuration baseline is for any part of the system. For example, we would want to be able to see what the current agreed configuration of our kitchen appliances is and how this configuration has changed over time. This is called status accounting in configuration management. Speaking of change, a critical element of configuration management is the ability to be able to manage change. Change is not bad in itself, but change without adequate control and visibility is potentially disastrous. Imagine if the customer and architect kept making changes to the configuration baseline of the kitchen without involving the cabinet maker and the builder. Naturally, the cabinet maker and the builder will build the kitchen against their baseline, but the customer will expect the kitchen to be delivered against their baseline. Change management is all about being able to gather the appropriate parties together and look at change proposals. In this case, the customer, architect, cabinet maker and builder need to get together and discuss the proposed change. The cost and schedule impact of the change would be discussed, and a decision will be made based on whether or not to make the change. Either way, everyone is informed and the decisions are made based on accurate information, which is the aim of the change management process. Finally, configuration management also involves periodically auditing the process to make sure it's working properly. We've covered this before, but let's have another look at it. We need to check that everyone is using the agreed documentation in performing their work, and we also need to confirm that the material being used and the construction process being employed is in accordance with the design documentation. Hopefully, our audits will confirm that everything's working well. Poor audit results indicate that there's something going wrong with our configuration management systems. Poor audit results therefore warrant some investigation. For example, if our plumber is using pipes that are different from what the drawings specify, this could be caused by the plumber doing the wrong thing, or it could be caused by the plumber working from the wrong drawings. The former requires action against the plumber, whilst the latter requires tightening of our configuration management process.
If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.